Have you ever really stopped to think about how an idea in your head, just a concept, actually becomes a real app on your phone? I mean, how do we get these incredibly complicated machines to do exactly what we want them to do? Well, that's the journey we're going to take in this explainer. We're going to unpack the amazing story of how humans talk to computers.
And right away, we hit the fundamental problem. You see, at its very core, a computer is basically just a giant collection of switches that are either on or off. That's it. It's a black and white world of yes or no. So the real question is, how on earth do we bridge that massive gap between that super simple binary state and, the incredibly complex things we ask computers to do every single day?
To answer that, we really have to start at the very, very bottom. We've got to talk about the one and only language a computer actually understands on its own. And spoiler alert, it's not English, it's not Python, it's the language of raw electricity. This is what's called machine language, or machine code, and it is literally just a stream of ones and zeros that talk directly to the on and off states of the computer's circuits. Now, for the machine, this is fantastic. It's incredibly fast because there's no translation needed at all. But for a person, oh man, it's almost impossible to read or write. The problem becomes crystal clear when you think of it like this. Imagine trying to write a novel, or maybe just explain a simple recipe, using only the words yes and no. You might eventually get there, but it would be so painfully slow and you'd make a ton of mistakes. And that right there was the first major hurdle in computing. So obviously, the pioneers of computing needed a much better way. They started to build what we can think of as a ladder of abstraction. Basically, a series of steps designed to get us further and further away from the machine's ones and zeros and closer to a language that humans can actually understand. The very first rung on that ladder was something called assembly language. And this was a really groundbreaking first step to make programming more human-friendly. It created this crucial buffer so people didn't have to write out endless, mind-numbing strings of binary digits by hand. So instead of ones and zeros, programmers could suddenly use these short, memorable codes called mnemonics, things like move to move data around, add to add numbers, or sub to subtract. It was a huge improvement, for sure. But there was a big catch. This code was still really technical, and it was tied directly to one specific type of computer. You couldn't just write assembly code for one machine and expect it to work on a different one. No way. The next step up that ladder, well, it was completely revolutionary. This is where programming really started to look less like some cryptic technical jargon and more like something we could actually read and understand. Welcome to the era of high-level languages. High-level languages were a total game changer, mostly because they use familiar English words and mathematical symbols we all recognize. All of a sudden, code became readable. But even more importantly, these languages were machine independent. You could write a program one time and, with the right tools, run it on all sorts of different computers. This is the category where all the languages you've probably heard of live, like Python, Java, and C++. Now, at the very top of our ladder, we find the most user-friendly languages of them all. These are often designed for really specific, super powerful tasks, like managing gigantic databases. And the whole goal is to make programming as effortless as possible. The philosophy here is a major shift. With languages like SQL, which is used for databases, you don't write out every single little step. Instead, you just describe the result you're looking for. And the computer itself is smart enough to figure out how to get it. We've gone from telling the computer how to do something to just telling it what we want. It's a huge difference. But hang on a second. If the computer only understands machine language, just those ones and zeros, how does it understand Python or C++? Well, the short answer is it doesn't, not directly. We need a middleman. We need a translator. The process is actually pretty straightforward when you break it down. A programmer writes code in a language they can understand. Then a special translator program takes that code and converts it into the ones and zeros that the computer can actually execute. It's that simple. But all the magic is in how that translator does its job. Okay, so one type of translator is called a compiler. What a compiler does is take your entire program, all of it, and translate it into machine code in one single go, creating a brand new, ready-to-run file. A really good way to think about this is to imagine a compiler is like proofreading an entire essay before you even think about handing it in. It scans the whole thing from top to bottom, all at once and checks for any mistakes. If it finds any problems, just gives you a big list of everything you need to fix before it will even try to run. So what's the key takeaway here? It's all about raw speed. Because all that translation work is done up front, the final program runs incredibly fast. This is exactly why languages like C and C++, which are used to build things that need every ounce of performance, like video game engines or your computer's operating system, almost always use compilers. You know that smooth, lag-free experience you get in a game? Yeah, you can probably thank a compiler for that. The other main type of translator is called the interpreter. And you guessed it, it takes a completely different approach. Instead of translating everything all at once, it goes through your program line by line. A great way to get this is to imagine you're reading a book out loud. An interpreter reads one line of your code, translates it, runs it, and then moves on to the next one. But if it hits a line it doesn't understand, it just stops cold, right then and there. It has no idea what's coming next. It just knows it found a problem. Now, this actually makes finding and fixing errors a lot easier because you know the exact line where the program broke down. The trade-off, though, is that this line-by-line process is generally slower than a compiled program. But that flexibility is perfect for stuff like web development or data science, which is where languages like Python really shine. It's why a web page can load new information without a full refresh. There's an interpreter working behind the scenes in real time. Okay, so we've got our languages and we have our translators, but how do programmers actually structure their thoughts? I mean, how do they organize thousands and thousands of lines of code into something that actually works? Well, they use different kinds of blueprints. This really brings us to two big philosophies for organizing code. First, you have procedural programming. This is basically the cooking recipe approach. You write out a very clear step-by-step list of instructions for the computer to follow, from the top to the bottom. It's direct, it makes sense, and it works great for smaller tasks. But if you're building a huge, complex app, a single recipe with a million steps would be a total nightmare. And that's where modular programming comes in. This is much more like building a car. You don't build a car in one long sequence, right? You build the engine, the wheels, the electrical system, and the body as separate, independent modules. Then you put them all together. This approach is incredibly powerful for big projects because different teams can work on different modules at the same time. And hey, that engine module you built, you can reuse it in another car later. It's all about organization, reusability, and just taming that complexity. So, as we start to wrap this up, let's just take a step back and appreciate the incredible journey we've just covered. At its heart, it's a story about one of the most powerful ideas in all of technology, abstraction. We started way back in the past, with programmers literally flipping switches by hand to represent ones and zeros. Then we started climbing, inventing simple codes to make life a little easier. And now, here we are in the present, writing in languages that are expressive, powerful, and honestly, in a lot of ways, kind of beautiful. We've built this amazing ladder that lets us stand high above the raw complexity of the machine so we can focus more on our ideas. And that, right there, leads us to the final, most important question. This entire history, this whole journey, has been about one thing: making it easier to translate a human idea into a machine's reality. And as that translation process gets even more seamless, the only limit left is the scope of our own imagination. So, what are you going to build?